distribute in order to eventually get a structure. Now, one of the ways that, one of the things we needed were these very, very powerful sources of X-rays, because ribosomes are very large molecules in molecular terms. And so the crystals of ribosomes don't diffract very well. That is, the spots are not very intense. And so you need an extremely intense source of X-rays. And these are some of the synchrotrons we use. This one is in France, these two are in the US, and this one is in Switzerland. So I like to joke that you can join a ribosome lab and see the world. This is a paraphrase of the US Navy's recruiting campaign, which used to be join the US Navy and see the world. But of course, these people are not actually going sightseeing. They're stuck inside a ship most of the time. And of course, my people aren't going sightseeing either. They're actually inside the synchrotrons all the time. So they're only seeing the world's synchrotrons, not actually seeing much of the world. And what they're seeing is something like this. This is the inside of a synchrotron instrumental touch. And this tube brings the X-rays from the synchrotron ring, and this is where the crystal is, and it's cooled. It's kept cooled by a flow of nitrogen at very low temperatures. And this is a CCD detector, which measures the scattered X-rays. So when you finish this experiment, and you've done it correctly, what you end up with is a three-dimensional image of the object you're looking at. And in our particular case, originally it was the 30th subunit of the ribosome. And this is what it looks like. Of course, the problem is this doesn't tell you what the atomic structure is. This is simply a three-dimensional image of the object, although in much greater detail than you would see otherwise. So how do you go about from this three-dimensional image to an atomic structure? That's a bit like solving a complicated jigsaw puzzle. But there are fundamental differences between an ordinary jigsaw puzzle and this kind of jigsaw puzzle. First of all, this is in 3 dimensions, not in 2 dimensions. The other problem is, when you do an experiment, there are always errors, and you don't know what those errors are. So you may see images where there shouldn't be any image. You may see part of an image where there actually should be empty space. Or you may see vice versa, there should be something there, but you don't see it, either because it's moving around, so it's blurred, or because of errors in your measurement. So it's like solving a jigsaw puzzle where the shapes don't always fit correctly. And you have to use knowledge to realize, okay, this is a region that isn't fitting exactly, and this is a region that fits exactly. And that takes a lot of prior knowledge. Of course, the most important difference is that when you buy a jigsaw puzzle, there's a picture of the puzzle on the cover of the box. So you already know the answer before you start solving the puzzle, whereas here we don't know what the molecule looks like, okay? And that's perhaps the most difficult thing of all. So what you do is you start looking for regions you can recognize. Just as in a puzzle, you would look at the corners and the edges first and build those, and then work your way into the more and more difficult parts. Here, what you'll do is you'll zoom around your object and see what you recognize. And if you zoom in, what you can see is here's a region where there's a regular repetition of these bumps. And on the other side, you can see an equally regular repetition of the bumps. And if you know your nucleic acid structure, you'd recognize these as phosphate groups connected by sugars. And in between these two strands would be these bases that are interacting with each other. And so what you would then do is build into the molecule, and you would thereby explain a piece of that image in atomic terms. You would interpret it in atomic terms. So what you've done now is taken that image and interpreted it in terms of an atomic structure, and that's what that structure would look like. But remember, this is only a small part of the entire image. You've built a small part of the whole image, and so what you then do is keep on building all of the parts you can recognize until you account for all of the image. And so that's what you do. First you ask, where is the part that I've built in the context of the whole image, and then you would gradually start building the entire image until you've accounted for all of the image. And that's when you realize you've actually solved the atomic structure of the molecule. Okay? And that's a very special moment in a structural biologist's life. So using that, Tom Stites' group at Yale had solved the structure of the large, or the 50th subunit, while we had solved the structure of the small, or the 30th subunit. And this actually shows that because the ribosome consists of both protein and RNA, it's about 2/3 RNA, and one of the most important things was it gave us a glimpse into what an early ribosome might have looked like, because today's ribosomes pose a dilemma. If the ribosome is used to make proteins, and the ribosome itself consists of proteins, where did the ribosome come from? Because if it's the thing that makes proteins, how could it be that it also contains proteins? Well, Crick long ago suggested that maybe early ribosomes consist only of RNA. And even today's ribosomes, the active site of the ribosomes, where the peptide bond is formed, or where the tRNA codon is recognized, anticodon recognizes the mRNA codon, consists entirely of RNA. The proteins are not involved in these very critical regions. And that strengthens the idea that an early ribosome may have consisted only of RNA and proteins got added later. Now here is a picture of the entire ribosome that we solved in 2006 with the tRNA and the mRNA ligands bound to atomic resolution. Now this brings me to the idea of how you could recognize antibiotics. I started off with antibiotics and how they bind to the ribosome. The point is that once you had a structure of the ribosome or its subunits at high resolution, you could actually then very straightforwardly determine the structure of an antibiotic bound to the ribosome. Because if you took the data from the antibiotic bound ribosome and subtracted the image from the free ribosome, what would be left is the image from the antibiotic alone. And I show you that over here. This is the image from the antibiotic alone, and that's obtained by using a difference technique. And you can see that this is interpreted now in terms of the antibiotic spectinomycin. And spectinomycin is very small compared to the entire 30th subunit, but the reason it can work is it blocks a very critical hinge point between the so-called head of the ribosome, 30th subunit, and the body. And this head is known to move with respect to the body. And so by binding at a very crucial point, even a very small molecule can block the function of a large thing like the ribosome. Now, there's a very clinically important antibiotic called tetracycline, which binds over here. But it turns out this is exactly where those tRNA molecules that bring in the amino acids bind. So if you have tetracycline here, it won't be able to bind to the ribosome, and that's why tetracycline stops protein synthesis. Now I want to close with a couple of things. One is, why do bacteria develop resistance? Well, there are several ways that bacteria can develop resistance. You can see that antibiotics work by having a precise pocket in which they bind to in a target molecule. So these ribosomal antibiotics will bind to the ribosome with a very precise pocket where they fit exactly. Now that kind of fit is necessary for the antibiotic to work. But you can break down that fit in several ways. One is this bacteria can make proteins which simply break down the antibiotics. If they break down the antibiotics, then they no longer are intact and can bind in a pocket in a specific way. The other thing they can do is have proteins that modify the antibiotic by adding groups. A typical group that they add is an acetyl group. So you have acetyl transferase enzymes which add chemicals to the antibiotic. And because they've now changed the shape of the antibiotic, it doesn't fit in the pocket properly. A third very common mechanism is that you have pumps in the bacteria that recognize foreign substances like antibiotics and pump them out of the cell so the antibiotics don't do any harm to the bacteria. So these are three completely different ways of acquiring resistance. The one thing that's guaranteed is that if you use an antibiotic, eventually bacteria will become resistant to it because of natural selection and selection pressure, which is very powerful. And so it's very important to use antibiotics wisely. If you want to develop a new antibiotic, and Tom Stites can tell you this much better than I can, because he founded a company called Rybex to develop new antibiotics, and perhaps he'll talk about that. To develop a new antibiotic costs over $1 billion because you have to do a tremendous amount of screening to identify new compounds. You have to be able to synthesize them, simply test for toxicity, for side effects. You have to see that they're actually working inside the human body. It's all a huge amount of work. It takes up hundreds of people's time for many, many years before something actually can be used in patients. So it's important to treat infections in other ways. One is you have to promote rational use of antibiotics. I notice in India, whatever the laws are, you can go down to a chemist or pharmacist or medical supply store and say, I want this antibiotic, azithromycin. And without questions, the guy will give you azithromycin, regardless of whether it's a proper antibiotic or not. Okay? Your friend might say to you, oh, I was sick and I took azithromycin and it was perfectly fine. So, next time you're sick, you should take that. That's not a good way to use antibiotics. Antibiotics should be highly regulated. And they should not be given for diseases that they are not effective for. Some antibiotics are better against certain diseases. They're useless against viral diseases. So you have to be careful about the use of antibiotics. The other thing you need to do is surveillance. One of the important things is to make sure that you identify TB victims, TB patients, people who have TB, and make sure that you've identified them. That takes public health and surveillance. If they have other diseases, for instance, elephantiasis is a bacteria. Elephantiasis is caused by a parasite, but the parasite has a symbiotic bacterium which is sensitive to doxycycline, which was recently discovered to be effective against elephantiasis. By killing off the bacteria, you indirectly kill the parasite. And doxycycline is also used as a malarial prophylactic, and it turns out it binds to the 30th subunit because it's a close analog of tetracycline. So again, if you identify, but it doesn't work against the later stages of elephantiasis where you've already done damage to the lymphatic system. So you have to identify when people have elephantiasis at an early stage, and that again takes surveillance so that they can be treated. You have to use infection control. This involves sanitation, prevention of, if you have an epidemic, you try and stop the infection. So those are all public health measures that are far more effective than developing new antibiotics because they're much cheaper than having to develop new antibiotics. But of course, we have resistant bacteria, so we always have to stay ahead of the game, and we need to develop new antibiotics. And that again has many aspects to it. We need